So we have a result that allows us to perhaps bypass the need to use the definition to compute the limit. As always, take the subset A and R, function A, R, C, limit point. Limit of the function f when x goes to c is L if and only if the limit when n goes to infinity. Now notice here we're going to sequences rather than talking about the function. The sequence f at xn is equal to L for any sequence xn contained in A such that xn is not equal to c for every n xn c. There's two directions in this statement. Start by showing. Let's assume that the function of the limit f when x goes to c is indeed L. That means that for every epsilon greater than 0, we can find a delta epsilon also greater than 0, such that distance between f at x and L is less than epsilon whenever x not equal to c, and distance smaller than delta epsilon, and x is set A. Now we will prove that the limit of f at xn when n goes to infinity must be L whenever we have such a sequence that satisfies these conditions. So let xn be a sequence in A with xn not equal to c and xn converging to c. Because the sequence of xn is convergent for the positive quantity that has been picked here, the delta epsilon, which corresponds to the epsilon, you can find an integer m, which depends on delta epsilon, such that this is true whenever n is greater than m delta epsilon. That is the definition of xn converging to c. Now this sequence of ours is such that the xn's are never equal to c, so that this bit here, which usually comes in the proof of the convergence of a sequence, we can also bound it below by 0. So pick n epsilon to be this m delta epsilon. Then f at xn minus L has to be smaller than epsilon, because f at x minus L is smaller than epsilon whenever you pick an x which is within delta epsilon of c, and all of these xn's here are within delta epsilon of c. So in particular, f at xn will be within epsilon of L whenever n is greater than epsilon. We've shown that this sequence here converges to L. For the other direction, we will use the contrapositive. So we're going to assume that the limit of the function f at x goes to c, is not equal to L. And we're going to show that there's a sequence xn which converges to c, but for which f at xn does not converge to L. And we will have proven the if and only if. The negation of definition limit tells us that there exists an epsilon 0 greater than 0, such that for every delta greater than 0, you can find an x delta such that the difference between x delta and c is smaller than delta, and this x delta here will be part of the domain of the function, but for which the difference between f at x delta and L is greater or equal to epsilon 0. But this is true for every delta. This is definitely true for delta equal 1 over n. Do this for every n. For every choice of n, I get a delta, then I get an x delta. X at n for us will be the x delta you pick for the specific value, delta being. What we have is a sequence of values which are all in A, and by construction, values at xn are all within one end of C, every n. And we also have that distance between f at xn now is greater than 0. Now the squeeze theorem here tells us this goes to 0, this goes to 0, so this goes to 0, is the absolute value of xn minus c goes to 0, which means that xn minus c goes to 0, which means that xn goes to c. All these xn's are in A, none of them are equal to c, but the limit of f at xn is not equal to L. Got an epsilon 0, such that blah blah blah. This proof will only make sense to you if you know or remember what the negation of the definitions are, right? When we write that the limit when x goes to c f at x is L, we are saying that for every epsilon greater than 0, there exists a delta epsilon greater than 0 such that f at x minus L is less than epsilon whenever x minus c, absolute value, is smaller than delta epsilon greater than 0 for values x are all in A, c being a limit point, so forth. Well, the negation of that statement, to say that the limit of a function is not equal to L, means the following. Exists an epsilon 0 greater than 0 such that for every delta greater than 0, you can find a specific x delta in A such that, on the one hand, this property is satisfied, but the desired conclusion is not. To be aware of how to negate definition. Well, this theorem that we just saw, theorem 26, is useful because it allows us to create the candidate value for L, to find it before we can actually show. Pick some sequence xn which converges to C, look at what the sequence f at xn looks like, see to what it converges, and then you have your candidate for the limit of the function. Consider the following function from R to R, which associates every x to the polynomial 3x squared plus x plus 1. It's the limit when x goes to 7. This function, well, pick any sequence xn which converges to 7, xn not equal to 7 for every n. The limit then f at xn will be the limit n goes to infinity of 3 xn cubed plus xn plus 1. And here you use the properties, sequences and limits to show that this would be 3 times the limit when n goes to infinity xn cubed plus the limit n goes to infinity of xn plus 1, which will be 3 times 7 to the third power plus 7 plus 1, independently of what the sequence would be. This would be 1087. Now, the sequence that we've picked here is completely arbitrary. We didn't specify what the xn's were. According to the theorem that we've just proven, this actually shows that the limit function, point, be 1087. But the fact that this was arbitrary is crucial. If you had shown that for a given sequence, for instance, I don't know, 7, let's start with, say, 6, 6.9, 6.99, 6.999, that goes to 7, and if you put that in here, then you wouldn't have shown that this is true for an arbitrary sequence. You would have shown that this is true for a specific sequence, and then theorem 26 could not be used. Consider this function. Function from the interval 2 to infinity into R, which associates to each x the following value. Show that limit x goes to 2, function f at x equal to 1. So, we pick an arbitrary sequence, converges to 2, where each of the xn's is different from 2, where, the xn's are n equal to infinity. Then f at xn be equal to xn minus 1 times xn minus 2 divided by xn minus 2. Because xn is never equal to 2, cancel these, becomes xn minus 1. So the limit when n goes to infinity, f at xn would be the limit when n goes to infinity of xn minus 1, which according to the properties would be the limit when n goes to infinity of xn minus. This is an arbitrary sequence. It goes to 2, 2 minus 1, 1. Because the sequence was arbitrary, what you've shown is that the limit of f at xn for any such sequence is 1, and so you conclude the limit of this function when x goes to 2 is indeed equal to 1. And you can show, using the same result, that the limit when x goes to 0, x squared cosine 1 over x is 0, because you pick an xn, sequence xn which converges to 0, which is never equal to 0 for every n. In particular, the xn's are in R minus 0. You look at f at xn would be xn squared cosine 1 over xn. And then you need to show that, well, what does this converge to? That one is a little bit less obvious. right? Because you have this problem. You can't just use the properties of sequences. So here you have to go and use the definition. Convergence of a sequence. For every epsilon greater than 0. Well, do you have to use this definition? I mean, you could, but in order to use a definition, you sort of need to know what the sequence converges to. You sort of know that it has to converge to 0 because we've computed the limit of this function previously. Let's see if we can come up with a way to compute the limit here without having to use the definition. I think you'll agree with me that xn squared cosine 1 over xn is stuck between 0, absolute value, and x squared, xn squared. Now this, when n goes to infinity, goes to 0 because you've picked sequences xn that go to 0. And 0 goes to 0, and you don't have a choice. What's inside here by the Squeeze Theorem has to converge to 0 in absolute value. If it converges to 0 in absolute value, it converges to 0 without the absolute value. Of course, this only works if what it converges to is 0. If it converges to something else. Up the creek without a paddle. But you don't need to use the definition of convergence of a sequence. Unless you use the definition of convergence of a sequence. Last example we'll do here. Function from R to R, which every x will either associate 0 or 1 depending as to whether x is a rational number or an irrational. What do you think the limit of this function is when x goes to 0? Well, the function is odd. This is definitely not a continuous function. Let's see if we can use a theorem. I'm going to pick two sequences. Here's xn, which will be the sequence 1 over n. That does converge to 0. Here's a new sequence, square root of 2 over n. It also converges to 0. You'll agree with me that neither xn nor yn are ever equal to 0. Now, what about the function, the sequence f at xn? So xn 1 over n, that's rational, so f at xn is 0, and this converges to 0 when n converges to infinity. And f at yn going to be 1 because yn is irrational. We've shown the square root of 2 is not irrational. So this converges to 1 when n goes to infinity. And now we have two sequences that both go to 0, none of which are ever equal to the limit point 0 in question. But the function evaluated at these terms give us new sequences which converge to two different values according to theorem T6. The limit here cannot exist. Now you might say, well, hang on. These values here are equal to their limits. Did we just spend a bunch of time talking about how the terms couldn't be equal to their limiting values? It's like, yes, when we talk about x and c, we talk about this chunk here. At no point did we ever say anything about f at x not being able to be equal to L, right? It's really about x approaching c. It isn't about f at x not being equal to L, because if you look at this function here, which is a constant function, as you see, you want values of x which could in theory be close to c without ever being equal to c, but the heights of these functions here are always going to be the same. And we would like this definition to also work for such a sequence. So be careful with the interdiction against xn being equal to c in these definitions of limits only apply to the limit point part of the definition, not to the function. So to show that a limit does not exist, it is sufficient to find two sequences which both converge to the limit point in question, but for whom the sequences of the values of the functions do not converge to the same value, L, right? Because we've shown that if a function has a limit at a given point, it has at most one. So we've identified two potential limits. The function cannot have a limit at that point. So to show that a limit does not exist, you can do this. Come up with a counter example. But to show that the limit exists, you need to pick an arbitrary sequence, not two specific sequences, which gave us different values. You see why it doesn't apply to situations such as this one, or even the bottom.